In this video, we're going to talk about finding concavity and inflection points for a function. So we saw that the second derivative tells us about the concavity of the original function. And the definition of concavity is that the graph of a differentiable function f of x is concave up over an interval if the first derivative, f prime of x, is increasing on that interval. And that's true if and only if the second derivative is greater than 0. So, for example, in the graph below, we are concave up over this area here because the first derivative is increasing. Similarly, we're still concave up over here because the first derivative, the slope, is becoming less negative, it is increasing. Over the interval here, maybe from about here forward, we are concave up over that interval in blue. And it's concave down over an interval if the first derivative is decreasing over that interval. So like here, for example, we are concave down because if we take 2 points over that interval, the first derivative, the slope of the tangent line, is becoming smaller. And you can verify that it is concave down over this entire interval and changes somewhere around there. So concave down. We also know that a point at which the function changes from being concave up to concave down is called an inflection point. So this right here would be an inflection point. And we saw that visually f of x is concave up over an interval if the tangent line to the function lies below the function. So for all those tangent lines in the blue area, the tangent line lies below the function, whereas it's concave down if the tangent line lies above the function. Another way to think about it is it's concave up if it would hold water, and it's concave down if the water would drip down the side. So those are some ways to think about concavity. Okay, so we want to test for concavity and inflection points for functions. For this, suppose that a function f of x has both a first and second derivative. Then the graph of f of x is concave up if f double prime of x is greater than 0, and concave down if f double prime of x, the second derivative, is less than 0. And if c f of c is an inflection point of f of x, then that can only occur when the second derivative is either equal to 0 or is not defined. So this is sort of like critical numbers for the first derivative. Remember that a function can only change from increasing to decreasing if the first derivative equals 0 or the first derivative is not defined. Here, we can get inflection points, places where the concavity changes, only at places where where the second derivative is 0 or the second derivative is undefined. So let's do an example. Let's find intervals over which a function f of x is concave up or concave down, and also find the inflection points for f of x. Let's look at f of x equals x to the 5th plus 5x to the 4th minus 40x squared. And to do this, we are going to first find the second derivative. Then we're going to make a number line separated by potential inflection points. Those are places where the second derivative equals 0 or the second derivative does not exist. We are going to test whether the second derivative is positive or negative over those intervals to see if the function is concave up or concave down over each interval. And if the concavity changes at a point c and f of c is defined, then c f of c is an inflection point for the function. So this is very similar to our first derivative test for increasing and decreasing functions and locating relative maxes and mins. So I encourage you to pause and try out those steps, and we'll talk about it in a moment. Okay, so first we want to find the second derivative. To find the second derivative, we first need to find the first derivative and then take its derivative. So f prime of x is 5x to the 4th plus derivative of 5x to the 4th is 20x cubed minus derivative of 40x squared is 80x. Then the second derivative is the derivative of the first derivative, so that is 20x cubed plus derivative of 20x cubed is 60x squared minus 80. And we know that potential inflection points occur where f double prime of x, the second derivative, equals 0, or f double prime of x does not exist. We see that that will not occur here because this is a polynomial, and so the second derivative always exists. Therefore, we're just interested in the places where the second derivative is equal to 0. So we can factor out a 20 from f double prime of x. We've got 20 times x cubed plus 3x squared minus 4 is equal to 0. So now we've got a trinomial. When is it true that x cubed plus 3x squared minus 4 equals 0? I won't ask you to factor trinomials, but let's go for it here. So this would have to factor into x squared plus or minus some stuff times an x plus or minus some stuff. We would also need a 4 and a 1 to be our last terms. It makes sense to have the 4 be a positive potentially, because we've got a 3x squared, so we don't really, we sort of have to do some playing around. Let's do a 4 there and a 1 here. So one of those has to be positive, one of those has to be negative in the end. And so one issue here is that we don't have an x term in this above, so those are going to have to somehow cancel out. Doing some playing around, you can let this be a negative, and if that is negative, then this must be positive. Again, we've got now a positive 4x, so to get rid of that positive 4x, we could add 4x here, and then we'd have 4x times negative 1. So let's just verify that this factorization works. So this was x squared times x is x cubed, x squared times negative 1 is negative x squared, 4x times x is a positive 4x squared, 4x times negative 1 is negative 4x, 4x times x is positive 4x, and 4 times negative 1 is negative 4. So these cancel, these combine, and we're left with x cubed plus 3x squared minus 4. So yes, this is the correct factorization of that above. And so can we factor it further? X squared plus 4x plus 4 is a perfect square. This is x plus 2 times x plus 2 times x minus 1 equals 0. So we've got 3 potential inflection points, or actually we've just got 2 potential inflection points because these are doubled. So x equals negative 2 is a potential inflection point, and x equals 1 is another potential inflection point. So these are possible inflection points, and we are going to divide up the number line over the whole domain of the function, all real numbers, with these potential inflection points, and we are going to test them in the second derivative to see if the second derivative is positive or negative. So our second derivative, f double prime of x, is, it was 20 times x cubed plus 3x squared minus 4. So that was our second derivative after we factored the 20 out. Now we want to pick points to test in that second derivative in between the potential inflection points. So some number less than negative 2, let's say negative 3, some number between negative 2 and positive 1, 0 is usually easy, and some number greater than 1, let's use 2 as the points to test. And so we're plugging these into the second derivative. F prime of negative 3 gives us 20 times negative 3 cubed is negative 27, plus 3 times 9 is positive 27, minus 4. And so we get 20 times negative 4, that's less than 0. And so this is negative, it's going to be concave down over this interval because the second derivative is negative. F double prime of 0 is 20 times 0 cubed plus 3 times 0 minus 4. So that's also negative. So we're also negative over this interval. It's concave down over this interval as well. And lastly, f double prime of 2 that's 20 times 2 cubed 8 plus 3 times 2 squared times 4 minus 4. So let's see there. That's going to be definitely a positive number. So I don't care exactly what the value is. I just care that it's positive. So it's positive, and that means that it's concave up over this interval. So summarizing, we see that the original function f of x is concave down, where the second derivative is negative, so from negative infinity up to negative 2, as well as from negative 2 to positive 1. At negative 2, the second derivative is 0, so we'd say no concavity there. And it's concave up on the interval from 1 to infinity. So what about the inflection points? So inflection points. So there is only one inflection point. There's only one inflection point. We see that this point x equals 2 is not an inflection point. That's not an inflection point because the concavity does not change. It's concave down before it and still concave down after it. But x equals 1 is an inflection point because it's concave down before and concave up after. So x equals 1 is going to be an inflection point for this function. And so to figure out the whole point, we'd want to plug it into the original function. The original function was f of x. The original function f of x was x to the 5th plus 5x to the 4th minus 40x squared. And so if we plug in f of 1, then we've got 1 to the 5th is just 1, plus 5 times 1 minus 40 times 1, 1 squared. And so we've got 6 minus 40, that's a negative 34. So our only inflection point is the point 1 comma negative 34. That's the xy pair of values for that inflection point. All right, let's do another example, and let's do the function f of x is the natural log of x squared plus 9. So again, for this example, let's find the concavity, the intervals over which this function is concave up and concave down, and let's also find the inflection points, So try to find each of those, and we'll talk about them in a moment. All right, so for finding each of these, we're going to take the second derivative. So first, we need to take the first derivative, f prime of x. The derivative of natural log of something, we're using the chain rule, where this is the inside function, and natural log of that is the outside function. So natural log of something, that's 1 over that something, x squared plus 9, multiply by the derivative of the inside. The derivative of the inside function is 2x. So again, we're using the chain rule to get that. And so we could rewrite that as 2x over x squared plus 9. All right, so that's the first derivative. We also need our second derivative, f double prime of x. For this, that's a quotient, so we'll use the quotient rule. So low x squared plus 9 d high, derivative of 2x is just 2, minus high 2x, d low, derivative of 2x plus 9, of x squared plus 9 is 2x, divided by the bottom squared. So that's the derivative. We're going to want to figure out the places where the second derivative is either equal to 0 or not defined. So to do that, we probably want to simplify this expression. So let's simplify. 2 times x squared plus 9 gives us 2x squared plus 18, minus 2x times 2x is 4x squared, all divided by x squared plus 9 squared. So then when we continue to reduce, we have 2x squared minus 4x squared, that's a negative 2x, so 18 minus 2x squared, divided by x squared plus 9 squared. So where does this second derivative either not exist or equal 0? So we're looking for the critical points, and we know that those critical points or critical numbers are either places where f double prime of x equals 0, or f double prime of x does not exist. Well, this would not exist when the denominator equals 0, but notice that this denominator, x squared plus 9 squared, well, it's always greater than 0, right? It's always a positive number squared. It's always going to be greater than 0. So that's not going to happen for us for this example. But we can figure out where are the places where the second derivative is equal to 0. So we will figure this out for the critical points. So the second derivative is equal to 0. This fraction is equal to 0 when the top is equal to 0, when 18 minus 2x squared equals 0. So let's solve that equation for x. So 18 minus 2x squared equals 0. If and only if 18 equals 2x squared, add that to the other side. If and only if 9 equals x squared, we divided both sides by 2. And if we take the square root of both sides, then x will be either positive 3 or negative 3. So x equals positive 3, x equals negative 3 are our critical numbers. Or, sorry, those are really our possible inflection points. So those are the possible inflection points for this function. Now to find concavity, we are going to make a number line where we put on the possible points of inflection, negative 3 and positive 3, and we're going to test values in the second derivative. So the second derivative, f double prime of x, we saw simplified to 18 minus 2x squared divided by x squared plus 9 squared. And so we are going to test points in the second derivative that fall between these intervals. So we could test, say, negative 4 is less than negative 3, 0 is in between 3 and negative 3, and positive 4 is greater than 3. So we're testing these points in the second derivative, f double prime of negative 4. Well, on the top, that's 18 minus 2 times 16 times 4 squared divided by x squared plus 9 squared. We don't really care, it's just a positive number. So what have we got? We got 18 minus 32, that's less than 0. This is negative, so it's going to be concave down on that interval. F double prime of 0 is 18 minus 0 over, again, the denominator is always positive, so this is going to be greater than 0. And f double prime of positive 4, that's going to be 18 minus 2 times 4 squared again, minus 2 times 16 over a positive number. Again, the top is negative, the bottom is positive, so this is less than 0 again, so concave down over that interval. So we see that this function is concave down on the intervals from negative infinity up to negative 3, as well as from 3 to infinity, and concave up over the intervals from over just the interval from negative 3 to positive 3. So that is the concavity of the function, and we're also interested in the inflection points. So we see that both negative 3 and positive 3 are going to actually be inflection points. These are both inflection points because the concavity changes. So these are both inflection points because the concavity changes. Before negative 3, we're concave down. After negative 3, we're concave up. After positive 3, we're concave down. So inflection points at x equals negative 3, x equals 3. To find the full value, we want to plug those into the original function. So our original function was f of x equals the natural log of x squared plus 9. So when we plug in f of negative 3, we have the natural log of negative 3 squared plus 9. That's the natural log of 9 plus 9 of 18. And f of positive 3 gives us the same thing, the natural log of 3 squared plus 9, the natural log of 18 again. So we could just leave those points as they are, that our inflection points for this function are negative 3 comma natural log of 18 as well as positive 3 comma natural log of 18. And that's just fine. I would probably just leave it as those. You could also calculate those using a calculator and find an exact value. If you do that, you'll find that natural log of 18 is approximately 2.89. It's an irrational number. It goes on forever, but it's approximately 2.89. So again, remember, natural log and e are inverses of each other. So what that means is saying e raised to what power is 18. This is saying that e raised to the 2.89 is 18, or e is approximately 2.718. Again, that's an irrational number. To the 2.89 is approximately 18. So that's, again, what natural log means. But we can also just leave it as this if we want.